So what we want to do now, as we've been talking about area, is move from the approximations. Okay, so approximations of RAM, all the different RAMs, the trap, the simp, to the more exact. And we are going to see how calculus can help us find the exact value of the area using an integral. And so we'll talk about how to define an integral, the notation and the terminology, and then the connection that those integrals make to the ideas of area. A Riemann sum is basically, I always think of R with rectangles. It is the sum of either defined or infinite number of rectangles. And we're looking at the area. And so we use the sigma notation. So that's the Greek sigma, which means summation. We go from the first rectangle to a specified number of rectangles, and we're going to add up the area. And so each of the areas is going to be a height times a base. So the first height times the first base, and then the second height times the second base, etc. You're working your way through. Typically, all of the bases should be equal. It's the heights that will be different, okay? And so then what makes it more and more accurate, well, we'll see, is that we're going to be doing the summation of the heights, and the heights are following the f of x, and then times a common base. That common base is delta x. So we use the Greek. Okay, we've got sigma, and then we have delta x. That's consistent, the delta x, every single time. Now we want that base to be as small as possible. And the way to make the base as small as possible is by making sure that we have infinitely many rectangles. And so we're going to have, as our rectangles go from rectangle 1 to rectangle n, we're going to have n approach infinity. So that is going to give us the most accurate way. Now it's key for you to understand that this constant is found by taking the bounds of b minus a, so that's the length of the entire interval, and dividing it by how many you have. And so that's a fixed value. And so if your n is really high, then of course your constant is going to be really, really low, really small. And that's the idea. We want it to be as small as possible. So as we define this, we have to be working with a couple requirements. We need it to be continuous. We need a closed interval. Okay, so starting at A, ending at B, broken up into n number of sub-intervals. And then that delta x is calculated as b minus a divided into n parts. And so then by defining the Riemann sum and adding the limit to that, that limit then converts it to an integral. That is the definition. And so when you just have k equals 1 to n of the height, which is following the curve, they have c sub k, we could have x sub k, however you want to do that, delta x. That by itself is just called a Riemann sum. When you say that there are infinitely many of those, that is what will convert that into an integral. An integral whose bounds go from a to b, following the curve f of x, and then we use the differential notation that Leibniz came up with instead of the Greek notation. Okay, those things are all equal. You should be, I'm sure that you're very comfortable with that notation, the integral notation. You should be as comfortable with this notation, knowing that those two are equal. So all the pieces have a different name, right? We call it an integral. We have the integrand. Okay, the integrand is the function that you're working on. The variable of integration is x. We call it from a to b. And so just the language, you should, you guys, we read that as the integral of f from a to b. And it's respect to, in this case, the x-axis, because x is the variable of integration. So now that you're in BC Calculus, you should be able to be as familiar with this notation as you are with an integral notation. So you should be able to go back and forth one to the other. What I usually find most helpful is to actually start here. That is the length of every base. And 6 minus n should coordinate to b minus a over n. And so my bounds, okay, does that mean my bounds are 0 to 6? Okay, could be. Does it mean my bounds are 1 to 7? Does it mean my bounds are -1 to 5? Okay, all of those are a length of 6. And so make sure that you are discerning when you read the question. Either they're going to give it to you or they are going to draw the graph for you. Okay, one or the other. So now we know that our bounds here are going to be -2 to 4. Our function is 3x squared minus 2x plus 5. And then we are working relative to the dx term. And so as you convert from the limit notation, the Riemann sum notation, into an integral notation, notice that the number 6 is not anywhere in the integral itself. The number 6 came from the space or the distance between the bounds. And so, you're not going to see a number 6 in your integral like you would in the limit notation. So this expression right here, like what does that mean? How do you write that in an integral form? All right, so let's see what we can do. This is not going to be approaching infinity because we have this divided differently. So this term, you're more likely going to see it on this end, but either way, it's okay, it's all right. It doesn't matter if it's on the front or if it's on the back. And so what I need you to recognize is that 1 over 20 is the b minus a over n. This is the common base that each of these have, okay? And so we need to know that the b minus a terms, the bounds on the integral, have to be spread out by 1. And so the most common is just to assume that we are 0 to 1. And so then these things need to be cut up into 20 pieces. And so if you look at all of the radicals are increasing by 1/20th each time. And so since my interval goes from 0 to 1 and is chopped into 20 pieces, then each of those is just, there's no difference between the base and then what I plug in. So this is just the square root of x. It's not the square root of x over 20. It's the square root of x because I've got 0 to 1. And this first one, which is 1/20th, the height is the square root of 1/20th. So it's the square root of what the x position was. And if I would fast forward and I'd get to 9/20ths here, which is the x position, the height is going to be the square root of 9/20ths. So it's the square root of whatever x is. And then we're doing that relative to the x-axis. So that Riemann sum, that Riemann approximation, is equivalent to the integral from 0 to 1. So notice there's no 20s anywhere. It's very simple. It's simply 0 to 1 20 pieces, spread up in 20 pieces out under the square root curve. Okay, I'm following the square root curve. All right, just like we had rules in differential calculus about things being important to be continuous and things being important whether or not they're differentiable, we can make the assumption here that all continuous functions are integrable, is the word that you use. If the function is continuous, then you can find the area underneath it. That's what it means to be integrable, that you can find the area, that the area is defined. Notice that differentiability is not key here. You can find the area under a corner. You can find the area under a cusp. You cannot find the area under an asymptote, but that's not continuous, right? So as long as it's continuous, you should be able to find the area. We define area as being relative to the x-axis, so we can have negative area, we can have positive area, and so you can have area above the x-axis and then subtract the area below the x-axis. We've talked a lot about that last year. When f of x is less than 0, in other words, when it's below the x-axis, then you have negative area. And so you'll have positive area as long as it's above the x-axis. And the area in this case would be the distance from B to A. So the base is B minus A, and the height is just C. So that's a positive value. Whereas the other one is below the x-axis. And so you'll have the base is still B minus A, but the height is negative C. And that will be the equal to your area. Okay, so for now, we are only thinking in terms of area. And so what this integral is asking you to do is to evaluate the area under the curve from, or the linear function, I guess, 7x. And so we have 7x is going to cross the x-axis at 0. We're going from -2 to 5. And so this is going to go from -14, that's 7x, to 35. So thinking of this only in terms of area, let's see, I'll put my 35 right here. We've got negative area, and then translating into positive area. So this integral would be -14 plus 35, and then you just add that up, right? So you get 21. You should be able to do it with rectangles, you should be able to do it with triangles, you should be able to do it with other functions that you recognize. And so this function in particular is a semicircle. You can tell it's a semicircle because this is a perfect square. Because it's subtracted, because you have a square root, all semicircles are r squared minus x squared, and the square root of that term, because it comes from x squared plus y squared equals r squared. And when you get y alone, you subtract the x squared from both sides and then apply the square root, which would give us a plus or minus. The plus or minus would be the full circle. If we just have the positive side, we're looking at the top half of the semicircle. If you have the negative part, you're looking at the bottom half of the semicircle. So if we're evaluating this graphically, okay, visually, graphically, we have a semicircle with radius of +2. So that will stretch to -2 and it'll stretch to +2. But we also have this +2 here, which shifts the entire thing up a unit of 2 as well. And so we're going to be shifting up my semicircle. Okay, so that is the shape that we are looking at. Okay, but even more particular, we're looking at where the boundaries are. And so we're looking at, oh no, it's not really the whole thing. It's half of it. So I'm going from 0 to 2. And what I've got is I've got a quarter circle on top of a square. So you'll need to recognize the different shapes. Okay, that this is a square that's 2 by 2. And then you have your quarter circle on top of that. So we are looking at area of 2 by 2, which is my square, plus the quarter of pi r squared. So this will be 4 plus a quarter pi times 2 squared, or 4 plus pi is the exact value of the area. Here's another semicircle, but it's inverted. Okay, another semicircle that's inverted, so we want to think about what that would look like. So again, if we're at 0, -2 to +2, and we're shifting this up 2 as well, except this time we're looking at a semicircle that looks like that. Okay, it touches the origin, sorry about that. And so we want to know, okay, well, what's the area of that piece? And so we are looking graphically, this area right here from 0 to 2. So the way I think of it is I think of first the area of the square. So that would be a 2 by 2 square. And then I want to subtract the area, and that's another quarter circle. And so I'll be taking away a quarter of pi times 2 squared. So we're looking at 4 minus pi in this situation to represent the yellow area going on here of what the area is that's left beneath that. Okay, the area that is bounded between the x-axis and this inverted semicircle, quarter circle actually, that's been moved up to. So not only should you know rectangles, triangles, trapezoids, circles, semicircles, you should also be comfortable with the branches or the waves of sine. So by definition, a sine of amplitude 1, that would go up to pi here, is going to have a bounded area of 2. So if we just want to think of that geometrically right now, we're looking at a bounded area of 2. We can prove that with an integral, with Newton, with Leibniz, but we're going to stick with that being the value of 2. So then if we want to do cosine, we're going to think of it in the same way. If we go cosine 0 to pi, that has a different shape. So the cosine is going to start with an amplitude of 1, and then come down to pi. So there's our 0 to pi. This has positive area, but it also has negative area. And so we have positive area of 1, we have a negative area of 1. So this would give me an integral value of 2 as the positive and negative areas cancel each other out. You should also be able to move these sine graphs sideways, translating them, or you should be able to move them up and down, or even reflect them upside down and still be able to manipulate the area to figure out what that value is going to be. Okay, finally, in addition to doing area by graph, we also today are just going to review how to do the area on your calculator. So if the graph gives you a function that does not give you a nice shape, it's not a circle, it's not a rectangle, it's not a branch of a regular trig function, not a regular wave, then you're just going to use your Math 9. So we got to just remember that Math 9 should pull up a nice integral for you, and then you can go ahead and enter this. But just make sure that you are in radian mode, especially if you're taking AP Physics right now. Make sure that you have radian mode. So you'll get the little boxes for you to fill in, and then you'll fill in what the function is, and then it will give you D blank so that it knows what axis that you're relative to. So you should be able to just grab that and type that in. If you ever do use Math 9, you must have written down the full integral somewhere on your paper, your quiz, your test. The full integral in its proper form must be written to get those points, and then you're welcome to use your Math 9 to evaluate, which in this case is going to give us a 2.0427, so we'll round that to 2.043. All right, there you go. That's what you'll be doing with integrals, geometry, graphically, and using numerically using the feature of your calculator. Okay, thanks.